Today, I will be discussing a paper that I have already published in the ICCIT 2022. So, the paper title you can see here that it is Human Activity Recognition Utilizing Ensemble of Transfer Learned Attention Networks and the Low-Cost Convolutional Neural Architecture. So, from the title, you can see some of the aspects that we are going to talk about. Firstly, we will be doing the human activity recognition and we will be using the ensemble technique and what we will be ensembling, we will utilize some transferred learning methods and where we will be also attaching the attention networks. And also in the ensemble technique, we are including a low-cost convolutional neural architecture. So now that we are clear about our topic, let's discuss about the outline here and then move on to the topics one by one. So the authors of this paper were myself and my respected colleagues S.M. Mehdi Hassan Bhaiya, Muhammad Farukuzzaman Faruk Bhai, and Abu Said sir, as well as Muhammad Ali Hussain sir. So, as you all know, that I'm Muhammad Azmain Yakin Srizon, and I am currently working as a lecturer in the Department of CSE RUET. So, I will be presenting this presentation. Okay, so let's talk about the presentation outline. One by one, we will go through the introduction, literature survey, dataset description. The proposed methodology will be discussed after that. Then we will see the results and we will analyze the results. And then we will talk about the conclusion and future scopes. However, I will be more focusing on the proposed methodology section, that how we thought about the architecture or why we went with these types of methods like ensemble learning and then attention networks and low cost convolution. So I will share the ideas. So first of all, let's talk about the human activity. All those that are all those activities that are carried out by humans are called human activities. So here you can see some examples like fishing, skating, motorcycling, badminton, like playing badminton, horse riding, exercising, or climbing. These all are the human activities. And there are so many applications of human activity recognition. I mean, where you can apply the human activity recognition. For example, you can use it in education, in medicine, in entertainment, for security reasons, from human monitoring or surveillance monitoring to in medicine like fall detection or other sorts of uh, applications like that. We can use human activity recognition. So here is a short literature survey. Um, the main thing is that uh, you can recognize human activities from various types of data. For example, you can utilize the video data, but it's very easy to recognize from the video data. For example, you can detect if there has been occurred, if a fall has occurred. You can do that by only analyzing the video. It's pretty easier, but it's difficult to recognize the human activities from still images. So what do I mean by still images is a single frame. You have to predict what activity a human is doing from a single frame. For example, from a single frame, it's very difficult to say if a person is walking or running, but it's very easy to say this thing from a video. From a video, you can just detect the motion of the human and say if he is walking or running. So not many researches, that have been conducted before were on these still images. So in this specific research paper, we have focused on those still images and try to establish a generalized model that can, recognize the human activities for different data sets for this type of still images. Okay, so now I will be talking about the data sets that I have used here. So the first data set that have been used here is the Stanford 40 actions data sets. So it has 9,532 photos and per class samples were 180 to 300. So it's an imbalanced data set. And there are 40 classes, obviously. That's why it's called Stanford 40 actions data set. Then the next data set is the BU101 data set. And as the name goes, there are 101 classes. However, we can break these 101 classes into five, broad categories. And you can see the categories: sports, body motions only, playing musical instruments, human-human interaction, human object interaction. These are the broad categories. And there are a total sample of 23,800. So it's a big data set. Okay, and here is our third and last data set that is called the Willow data set, which has 7 classes. And you can see the class levels like interaction with computers, taking photographs, activities of music playing. And there are 911 photos. So it's not a large data set, but yes, we can see some variations among the classes here also. Okay. So here is the basic proposed methodology. At first, we will be talking about the abstract view of the architecture, and then we will be exploring, or we will be amplifying each section to understand more how they are working. So first of all, you can see that the whole architecture is divided into two parts. First of all, we are taking a RGB image with a size of 224 into 224, and we are feeding this image to three transfer learning networks. We can see that in the first network we have used is DenseNet 201, and the second one is Exception, and the third one is EfficientNet V6. Now you may ask why these three only. So here is the basic reason, because DenseNet 201 architecture is very close to our brain, which is which has densely connected neurons. Then exception is the extreme inception. So we are utilizing the core concept of inception here also. And EfficientNet V6, as we know that it's better to support the scalability feature. So to support all these ideas, we have selected these three transfer learning methods. And after each of those transfer learning models, we have utilized a channel attention module. So it's an interesting topic. We will be discussing the channel attention module by amplifying it in the next slide. And after the channel attention module, the output is passed through the max pooling layer, obviously, and then followed by the dense layer, followed by the dropout. We know that we use the dropout technique to, reduce the overfitting problem. Then we applied the flatten technique, and then we concatenated all the features. Then we have simply used the final dense layer followed by a 50% dropout. Then we have the output layer with the softmax activation function. So apart from the output layer, everything else has the ReLU activation function. Okay, but this is the first part. And if you look at the bottom of the architecture, you can see the second part, where we have used a low-cost convolutional neural network, and it has an input size of 28 into 28, and it's a grayscale image. It's not a RGB image. So we are not only taking the features extracted by the transfer learning architectures, or only the features produced by those models on the top, but also we are taking the features produced by the low-cost convolutional neural. So in the next slides, first we will discuss about the channel attention module, and then we will be discussing about the low-cost convolutional neural network and how we come up with those ideas. Okay, now let's talk about the channel attention networks. So here you can see that we have utilized first the max pooling layer, followed by a dense layer that has a size of n by 8, and followed by a batch normalization layer. We know that we use the batch normalization layer to reduce the or overcome the gradient vanishing problem or covariate shift problems. Then we have also utilized another dense layer of size n, and followed by another batch normalization layer, because there is a fear of gradient vanishing problem or covariate problem here. Then followed by a dropout to reduce the overfitting. And then we are getting the channel attention vector. Now, what is this channel attention vector? The channel attention vector is basically providing us the information that which channel is how much important. So suppose if value in this vector is higher, that means that that corresponding channel is more important to us than the other channels. And you can see here that the size of input feature map is n channels, and the size of the channel action vector is also n channels. So these are the same size matrices or same size vectors. So what we have done here is we have calculated the priorities here, the attentions, and we have the main input feature map. Then we are multiplying these two to get the final feature map. So that has been showed here as the weighted feature maps, which is also the size of n, obviously. So this is why this channel attention network is amplifying our performance. You will see that in the performance section or obtained result section. Okay, so and here is the proposed low-cost convolutional neural network. Now the question is why low-cost convolution? Because it has used very few parameters. It's only 2 to 3 million parameters here. We are utilizing only 2 to 3 million. Where we all know that mobile net architecture has 4.2 million parameters. So the number of parameters is lower here, but in the performance section you will see that it can achieve higher accuracy. The question is why, so that's why I will be sharing the ideas. So here you can see that we have first take the input size image, the image that has an input size of 28 into 28, and it's a grayscale image that we have already discussed earlier in the earlier slides. So you can see that we have created 3 branches. For now, only focus on the first branch. Uh, if you understand the first branch, then you will easily understand the second and third branch. So in the first branch, we have basically 3 convolution blocks. So this one is the first convolution block, which has 2 convolution layer with the size of 32. So what do we mean by the size 32? By size 32, we mean that there are 32 filters in these convolution layers. So for the first convolution layer, we have 32 filters. For the second one, we also have 32 filters. Now the question is, what is the size of the filter? So here you can see that by the blue block, we means 3 into 3 convolution layer. That means the filter size is 3 into 3. So what we are doing here is we are utilizing 32 3 into 3 size filters here, followed by the same thing, the same convolution block with the same, configurations. Then it is followed by a max pooling layer. And what is the size of the max pooling? It's 2 into 2. Here you can see that. Okay, then what we have done, we have, created another 2 sub branches here. You can see here that this one is the first sub branch and this one is the next sub branch. So in these both sub branches, we have actually utilized 2 convolution layers just like before. But this time we have utilized 64 filters each. You can see here, here is the first convolution layer, here is the second. And in the next sub branch, you can also see that 2 convolution layers. And this one is the max pooling layer, and these are the dropouts. Now here are 2 major differences. In the first one, you can see that we have used orange block here or reddish block here. So what is this block? This block is basically batch normalization. And in the previous slide, I was saying that where we have the fear of gradient vanishing problem or covariate shift problem, we should use the batch normalization. So that's why we have utilized the batch normalization. But you can't see the batch normalization in the second sub-branch. Then you may ask, why is that? We are already using the batch normalization. So why do we need an additional sub branch that doesn't use the batch normalization features? So this is because sometimes the gradient is not vanishing, rather the gradient is very high. If we apply the batch normalization, then what it basically do, it normalize all the gradients. So the gradient that is very high, that has a high value, that is normalized to 1 if we do the 0, 1 normalization. And the other gradients goes close to zero or they get vanished. So by using batch normalization, we are trying to reduce those problems, but we may arise these problems in some cases. So that's why we created these two paths so that we don't neglect any one of them. And you can see that in the first sub-branch, we have a dropout value of 20%, but in the second sub-branch, we have a dropout value of 25%. Why? Because in the first sub-branch, we are normalizing the data. So, we are already solving half of the problem. That's why we think that we don't need a higher dropout value. And in the second sub-branch, as we don't have a batch normalization, we thought that we should integrate a higher um, dropout value, at least more than the first sub-branch. And our performance backed this idea up. You will see in the performance section. Then what we have done, we have concatenated those features and we have applied another convolutional layer. This time also we have utilized 64 filters and followed by a max pooling layer. Then here we have also used a dropout layer because we fear that overfitting will happen. Obviously, it should happen because the architecture is very compact. Okay, then it is followed by a flattened layer. So this one is the first branch, and in the next two branches, you can see the exactly same architecture. The only difference is that all the convolution layers that have been used in the first branch are of the size of 3 into 3. The filter size is 3 into 3. But in the second branch, all the filter sizes are 5 into 5. And in the third branch, all the filter sizes are 7 into 7. Now you may ask me why you are utilizing these three different sizes. Why, there are no other differences. The only difference is the filter size. Why you are utilizing this idea? This is because uh, we should use the shorter or smaller filter sizes when we are trying to distinguish between small features. But when we are trying to distinguish between larger features, then we should use the larger feature size. Otherwise, as a whole, the architecture will not be able to distinguish all the distinguishable features or the important features. That's why we have utilized three different filter sizes here. And you will see in the performance section that the individual branches performs lower than all the branches in a whole. So you will be seeing those performances very shortly. After getting all those features, we are just concatenating the features and it will go to the ensembling technique as shown on the proposed methodology. Now that all those ideas are clear, let's move on to the experimental setup. So first of all, we have set the batch size. The batch size for the transfer learning approaches was 24. And for the low-cost CNN, it was 256. And for the ensemble model, we utilized a batch size of 16. Learning rate was 10 to the power minus 5. The optimizer we have used, obviously, Adam, as it works better than the other optimizers. You can see that in the literature too. The loss function, we have used categorical cross entropy function as we are, dealing with the categorical variable. And the number of epochs were set to 25 because after 25 epochs, we saw that our model got, the model was stable. Okay, and the input size of the transfer learning technique, we have already said that 224 into 224 RGB images, and for the low-cost CNN, it was 28 into 28 size grayscale image. And we have a train validation test ratio of 60 to 20 into 20 for the Stanford Action dataset and the View 101 dataset. And for the Willow dataset, train and test were, provided separately by the authors. So here are the experimental outcomes. You can say that you can see that the DenseNet 201 architecture has produced a better accuracy among the three transfer learning approaches. However, the difference among the accuracy is not that much. You can see here. However, the custom low-cost CNN that we have utilized have, you can see here that it has produced better results than those other transfer learning approaches. So it's a great achievement, I think. Also, the proposed ensemble model has a very higher accuracy here also. Okay. So here is the comparison among the previous work and this work in terms of accuracy for Stanford 40 actions dataset. And here you can see that our proposed model has outperformed all the previous architectures, methods, or approaches by a significant margin. Okay, let's now talk about the View 101 dataset. So the past results that you have seen was for the Stanford 40 actions dataset, and this is the result for the View 101 dataset. You can see here the class-wise accuracy for each of the 5 categories, and you can see that in all those categories, the proposed ensemble model is working better. And if we compare the performance with the previous methods or approaches, you can see that in all the categories, our model is doing better. And here is the, so this one was the accuracy. This one is the precision, the comparison among the category wise precision. And this one is the results of the Willow data set. You can see the class-wise accuracy for all the 7 categories. And here is the comparison with the for the Willow data sets with the previous approaches or methods. Okay, so that's it. We have presented here our proposed architecture, and you already have seen all the performances, and I have shared all the ideas with you, that how we thought about those ideas and why we have utilized here. And from the performance section, you have come to see that our proposed model have outperformed the previous architectures by a significant margin. So that's our contribution. Now, what can you do? So what more are there to do? Here is an idea. So we are utilizing an ensembling technique here. So basically, when you are updating the weights of the architecture, as I have shown here, this thing can happen. What is this thing? So suppose your dense one architecture is doing very well. It is extracting very good features. However, the efficient net V6 is not extracting good features. But while you are training the model, suppose you see that your model is not doing that well. So what you will do, you will update the weights and you will try again. So while updating the weights, what you have done is basically you have made your efficient net V6 architecture more efficient, or it is now working better, but you have destroyed the integrity of the DenseNet 201 architecture. So DenseNet 201 architecture is not doing better at all now, but it was doing better before. So what we are basically doing, so while training, we are hampering the behavioral integrity of the models or the methods that we are considering here. To make efficient net V6 good, we are destroying the integrity of DenseNet 201 or exception or the proposed low-cost CNN architecture. So that is the main limitation of our proposed architecture. So how can we solve it? We can solve it by, first training each of the models separately. And then while ensembling these models, we can freeze each of the models by loading the already trained weights, and then only train the final, ensembling architecture, the ensembling block. And then we should get a better result theoretically. So you can think about this in the future, and you may also contribute in this field or in the similar field as well. So best wishes to you all. Whoever want to work with this topic are most welcome. And if you need any help, feel free to mail me regarding this topic or any ideas. If possible, I will share ideas or discuss with you how you can progress in this topic as well. Okay, that's all. And these are the references that have been utilized to, make this presentation. And thank you. Best wishes for you all. I hope you all enjoy the passion of research that I enjoy every day. Thank you very much.